boundary layers and external flows. We might wrap this up today. Uh, we for sure will finish with the boundary layers, and then if all goes right, we'll also discuss external flows. So what do we have? Uh, what we did on Friday, we took a look at boundary layers for the case in which the thermal boundary layer penetrated much deeper than the viscous boundary layer. So in that case, I we looked at a control volume that slid down together with the flow, is what in proper terms is called Lagrangian control volume. And we saw that in that condition, this control volume was behaving very much the same as the semi-infinite solid, and with the boundary conditions that could be of constant surface temperature or constant heat heat flux imposed on it. So we looked at the case of constant heat, surface temperature, and we used the same formula that we used for semi-infinite solid. That is this formula we have here. And we said, okay, because the fluid is moving downstream at a constant velocity, that is the velocity of the fluid far from the plate, u infinity, we have this relationship between space x and time t that was really through this the flow velocity. So we could replace this alpha t by alpha x over u infinity. X over u infinity is time in Lagrangian coordinates as we go downstream. And based on this, we could estimate age or the Nusselt number, right? Because we had the thickness of the boundary layer. And that's what unlocks all these calculations of convection, is let's get a thickness and of the boundary layer. And based on that thickness, then we can calculate the heat flux, because convection in reality is conduction through the thickness of the boundary layer. Okay, so we then saw that the boundary layer had a thickness that increased like parabolically, so very quickly at the beginning, and then keeps going as square root of x. We saw that because the convection coefficient is inversely proportional to the thickness of the boundary layer, the convection coefficient was very high at the beginning and would be lower downstream, right? And actually the equation says it's infinite, but of course we know it's not infinite. And the reason is that these considerations of boundary layer are assuming that the boundary layer is thin. But right here at the leading edge, or in this schematic of the plate, so let's see, here at the leading edge, it's we cannot say it's thin, it's just fairly the depth under which the fluid moved and and the heat of the transfer of heat are more or less comparable. We cannot say that the Peclet number is high at the beginning. So nothing, this is, we know it's not really infinity, but it behaves as very high and goes lower. We also saw that the way things are tabulated in books are in very, very general ways. And this is all the books, and there's a good reason for that. So they don't have tabulations for what is the h as a function of u infinity or something like that. Instead of h, they tabulate the Nusselt number. And this little x here means Nusselt using the characteristic length x. We're going to see that for cylinders, we are going to use Nusselt d. And it's going to be h d over k, and d is the diameter. Then instead of using u infinity, x, and those type of things, we use the Reynolds number, which you're familiar from your times in fluid mechanics. So see how we have been piling up dimensionless groups almost without wanting. We started with the Biot number, then we had the Nusselt number, the Peclet number. Now we have the Reynolds number, which we knew. We add up the Prandtl number. The Prandtl number is a ratio between the penetration of the viscous boundary layer and the thermal boundary layer. I'm saying this in a very rough way because we're going to see this very properly later in a couple minutes. So if I combine this expression of H by using Nusselt and Reynolds and Prandtl, it's just like changing the variables, the expression would be Nusselt is 0.564, Reynolds to the 1/2, Prandtl to the 1/2. And this is exact. And this is the really cool thing of what we saw on Friday, that we got the exact solution. And if you guys go to the book and you see how they treat boundary layer, you'll see that it's a system of 4 partial differential equations. 2 of those are the Navier-Stokes, which are equations that are nonlinear. Mathematicians make a living out of solving the Navier-Stokes equation. The guy who solved these Navier-Stokes equations for the boundary layer was a disciple of Prandtl, and I'll tell you more in a minute. So we also discussed the difference between local heat transfer coefficient and average heat transfer coefficient. So when we would say H of a window in the inside of a window in still air is more or less 10 watts per square meter Kelvin, there was an average. We were not that clear because we were still just trying to figure out what things are. But now we can say, okay, you want the local H or do you want the average H? Because we know that at the leading edge, when we have a boundary layer, is thin and the H is high. And as the boundary layer moves downstream, it gets thicker and the heat transfer coefficient is lower. And for the case of parabolic boundary layers, the relationship in parabolic, the laminar boundary layer is parabolic. For laminar boundary layers, we have that the average H is more or less twice the local H. Let's make a proper drawing here. So if we have our plate here, and we have our boundary layer, let's say thermal boundary. Something like that. Okay, so actually, let's make it better because I was using the thermal boundary. Let's draw H. Well, that's okay. That's the boundary layer. This is Y, C, T, and H. The heat transfer coefficient was something like this, and this is H. So if we pick a point here, let's call this point L, and this is the X coordinate, we would have that the average value of H, that this is local H of L, and this is local. And the average H over all this interval would be higher than that, of course, right? Because this part is much higher than this all other part. And what we see is that the H average between 0 and L is 2H of L. So H bar is the average. And this is equals to 2 times the local at point L. Most of the time, we're going to be using average convection coefficient. But when we get to natural convection, we're going to see how we can explain, for example, the fact that in a window, we get frost in winter when it's really cold, when we get frosting in the windows, we see the frosting at the bottom and not at the top. We will be able to explain that using local convection coefficients. Okay, so we made it up to this point. Now I want to have a bit of a refresher of the fluid mechanics, the boundary layer, the viscous boundary layer. So this is interesting. What we have discussed so far about the thermal boundary layer is very similar to the boundary layer in viscous fluids because both are transport problems. In heat transfer, we transport heat, which is a scalar magnitude. It's a magnitude that is just a number like energy. It's not a vector. In fluid mechanics, we transport momentum, and that is a vector. So it's not exactly the same, but there are enough similarities. And the overall equation is much of the same. What comes in minus what goes out, plus what is generated equals what is stored. That's the general equation of transport processes, which you're also going to be using when you study diffusion and mass transport. So both processes are very similar, fluid mechanics and heat transfer. And both processes have, both phenomena are characterized by a diffusion-like quantity. In the case of heat transfer was nu, that is the heat thermal diffusivity, nu. Alpha is thermal diffusivity. In fluid mechanics, you have nu, that is the kinematic viscosity, which both have units of meters squared per second that are units of diffusion, and both measure how we're diffusing either momentum for fluid mechanics or heat for heat transfer. The ratio between those two is a Prandtl number, such that if a material has low viscosity or high thermal conductivity, Prandtl number is low. That's the case, for example, of molten metals. If a fluid has a high viscosity and low thermal conductivity, such as oils, for example, the Prandtl number is high. And we're going to see that this matters. But for now, I'm just commenting on the similarity between the transport processes in heat transfer and fluid mechanics. Funny enough, you have something very similar to a Prandtl number for mass transfer called the Schmidt number, which you will see next term. All right, so this is interesting now. To solve the boundary layer in fluid mechanics, you need to solve 3 partial differential equations that are coupled. It's a nightmare. It's a problem that vexed mathematicians and physicists until the beginning of the 1900s. And that was solved. Solved by a professor and his student. The professor was Prandtl. The student was Blasius. And the stories are so cool that I uploaded those in additional material in the topics. I uploaded their bios. See, so if you're curious, nothing to do with exam, just in case you're curious, because their story is very interesting. Blasius did his PhD with Prandtl. His mission was to study the boundary layer, the fluid mechanic boundary layer, not the heat transfer one. So for partial differential equations, he had 3 partial differential equations. He hated it, beginning to end. You can read it in the bio, I uploaded it. When Blasius got his PhD and graduated, he became a teacher. He said, I don't want any more of this ever again. The story is interesting in itself. But why I tell you this story? Because we do not need to suffer what he suffered. We don't. We're going to use the 4 years of intense suffering of Blasius. In this case, I can tell you who was, Blasius, and how he said, I'm never doing this again. And in the end, his 4 years of life, here is what we get from the point of view, from what matters to us, that the thickness of the viscous boundary layer, this YCV, no, right, the characteristic distance in Y, right, the characteristic length in Y for the velocity or viscous boundary layer is 3 square root of nu x over u infinity. That's a formula he got. Interesting. If you remember, let's look at the similarities with our equation. Here we have, for the thermal boundary layer, we have alpha x over u infinity, and a square root of pi, right? And he didn't get square root of pi. He got a 3 square of nu x over u infinity. Nu and alpha, as we were just mentioning, are the metrics of diffusion of momentum in the case of fluid mechanics and diffusion of heat in the case of heat transfer. So those two equations are very much analog, very much analog. The square root of pi in heat transfer was for the case in which the fluid is moving as a block, right? We said that the viscous boundary layer is thin, and the whole fluid outside that boundary layer was moving as a solid. And we use the equation of the semi-infinite solid. Now, in the case of the viscous boundary layer, we cannot say that, because the viscous boundary layer has the whole gradient of velocities. That's in itself, right? That's its own boundary layer. If you spend the 4 years of Blasius and you suffer as much as Blasius did, you'll see that the answer is 3. What do you say? 4 years of life to get one number 3, but that's okay. At least for us, we don't need to worry. And if we were to do x over ycv, x over yct is the Nusselt number, the thermal boundary layer. X over the boundary layer, the viscous boundary layer, is nothing, but I put it as a comparison, and we get is 0.33 Reynolds to the 1/2. I'm just planting some ideas in your head here. We already talked about boundary layer thickness. In fluid mechanics, you might have seen it defined as 0.99 or 0.95. Typically, it's 0.99 of u infinity. That definition many people use, and the only problem is that we cannot do the math we do so much simpler when we choose the tangent, right? If instead of using the tangent, and instead of using tangent as we always do, instead of a factor of 3, we would get a factor of 5. Big deal. But ours is so much more insightful. So let's see, let's compare then, given that we have 2 boundary layers, a viscous boundary layer calculated by Blasius with infinite pain, and a thermal boundary layer, which we have calculated for one case, the case in which the thermal boundary layer is very thick, which we have calculated using semi-infinite solid at 0 pain, or infinitesimal pain, at least compared to Blasius. So this is what we got for the thickness of the boundary layer, this YCT equation here, for the thermal boundary layer when it's much thicker than the viscous boundary layer. We can compare with the viscous boundary layer and divide one by the other, right? And both have this alpha square root of x over u infinity. So if I divide one by the other, they would cancel each other out. The 1.77 was the one, the square root of pi. This 3 is the one that came from Blasius suffering. And if I do this calculation, it tells me that for the case when the thermal boundary layer is much thicker, the ratio between the 2 boundary layers is 0.6 Prandtl to the minus 1/2. Right, and this Prandtl had appeared before in our tabulation, right? What does this mean? So the ratio between the two boundary layers is this depends on the Prandtl number. Does not depend on the velocity, does not depend on anything other than the Prandtl number. And Prandtl number is the ratio between kinematic viscosity and thermal diffusivity. It's a fluid property. It's a fluid property. And if this number, thermal boundary layer, we said it has to be much bigger than the viscous boundary layer. So this has to be much bigger than 1. Therefore, because Prandtl is raised to a negative exponent, Prandtl has to be a very small number. That's metals, very small Prandtl number, right? And now we can compare the thickness of the two boundary layers. I mentioned when we started to discuss this, it took me, myself, a long time until I figured out why do we have more than a boundary layer and why is not a single boundary layer for everything? Now I understand, yeah, heat penetrates a depth that is different than viscosity. And sometimes it might be a lot more than viscosity, sometimes a lot less. So when it's a lot more than viscosity, this equation here is what is going to tell us the ratio. Okay, so for example, in the case of metals, and I'm going to get my calculator here, the Prandtl number can be 1,000, right? And 10 to the minus 3, right? If I have 10 to the minus 3, that would be more or less 1 over 30, right? And I multiply by 0.6. Let's see. Let's see. So we have and we have, like, in that case, we would have, if let's go here. If we have Prandtl is more or less 1,000, 10 to the minus 3 metals, right? The thickness of the thermal boundary layer is more or less than 0.6 times 1 over square root of 10 to the minus 3. And this is more or less 18. What do we get? In a metal, the thermal boundary layer is 18 times thicker than the case of than the viscous boundary layer. Let's see if I have a better drawing of the past trace we made. Okay, here. So in a molten metal, the thermal boundary layer, that is this one we have here, is 18 times thicker than the viscous boundary layer that we marked down here. So yeah, it's actually quite okay to say that we can forget about the viscous boundary layer thickness. Now, let's talk about the case in which we cannot forget about the thickness of the viscous boundary layer, because most of the time we're not dealing with molten metals, right? So let's see what happens. Let's start with a case in which the thermal boundary layer, the Prandtl number is 1. If the Prandtl number is 1, the thermal diffusion and the diffusion of momentum is the same, because they have the same diffusivity coefficients. Thermal diffusivity is same as kinematic viscosity. In that case, you can prove, and you can see it in the book, but these 4 coupled partial differential equations, when the alpha and the nu are the same, you can prove that the solution for the thermal boundary layer is the same solution, the exact same solution as the viscous boundary layer. So the heat transfer problem becomes Blasius problem. You can see in the book, it's just write the equations, and when you put like nu equals alpha, you see that you're solving twice the same problem. So we go back to Blasius. The fact that for the Prandtl number equals 1, the solutions are the same. This is what is called the Reynolds analogy. And it means that the fluid flow and heat transfer are the same thing in the case of Prandtl equals 1. So then we know that for Prandtl equals 1, for Prandtl exactly equals 1, we can say that the thermal boundary layer then is 3 square root of alpha x over uc, over the, in this case would be u infinity. Right? It's the same as alpha and nu are the same. And this is exact. So now we know the ratio of boundary layers for the case of thermal boundary layer much bigger than the viscous boundary layer. We know the solution, the ratio of boundary layers for the case the viscous boundary layer and the thermal boundary layer are the same. That is the case of Prandtl equals 1. How about now the case when Prandtl is much bigger than 1? How about the case when the viscous boundary layer is very thick and the thermal boundary layer is thin, which is the case of oils, for example, and we care a lot about oil here. So now this is a little bit more difficult. I'll try to make it as simple as I can, because in reality, although it's more difficult, it's difficult in the concept, but not the math. Math is never our issue here. So, oops. So here I have a schematic that I'll try to make on the left side again. And so we have our plate. And we have our coordinate system. This is X, and this is, ooh. And this is Y. And let's pick one spot. Let's pick this spot here, and we're going to make the graphs for the boundary layers. So I'm going to make them in a new page. So, but before I do it, so in this case, we have that the viscous boundary layer is thick. And the thermal boundary layer is thin. So I'm going to go to a new page to make this schematic that is here on the right, and let's do it together. So what I want to do here is to understand more than anything else. So let's see. I'm going to do the drain flip because we have been doing it flip many other so far in the class. Okay. So this is going to be our y-axis. And I'm going to make now my viscous boundary layer. And the viscous boundary layer, the horizontal axis would be velocity. Velocity is 0 at the surface. And no, I don't like it. Okay, let's make it better. So, right, and this is a free flow velocity u infinity. And if we use our tangent, as we often do, we do the tangent at the origin. Let's do it properly. Let's do the tangent here. And this intersection here is what is going to give us. This is yc of velocity. Now let's do the viscous boundary layer. And the viscous boundary layer, we said, would be, now the horizontal axis for the viscous boundary layer would be temperature. And we would have surface temperature. We would have the infinity. We're assuming that the surface temperature is higher than the temperature of the fluid. And so let's mark the points we know. And we said that the thickness of the boundary layer is much smaller. So let's say our thermal boundary layer is like this. And if we do our tangents, again, we would be doing our tangent from the origin, assuming it's straight. Okay, and this point here would be yct, and which is much less than ycv. So this is what we will do. And this is what unlocks something that is more complex than what Blasius did. And for all your pleasure, you can read it all in the heat transfer book. And even then, they don't tell you how they solve it, right? But I don't want to write multiple coupled partial differential equations unless I have to, and I don't have to. So this is what we will do. We will say that we will remember that Blasius' solution for the thickness of the viscous boundary layer is a boundary layer which accounted for this gradient inside it, right? You see, this is the thickness of the viscous boundary layer, and all inside the viscous boundary layer, we have a gradient. So that's the reason why instead of a square root of pi, like in the semi-infinite solid, instead of that, we got a 3. The semi-infinite solid is relatively easy, but means it's moving as a block. If instead of moving as a block, the fluid is moving in this, is moving in this direction, right? But starts to have this gradient here. You see the velocity here is less than the free stream velocity. And if I get closer and closer and closer to the surface, the velocity that is given by this segment is smaller and smaller and smaller. On the surface, the velocity is 0. Accounting for that gradient is a factor of 3. So this is what we will do. We will say we will account for the gradient in velocities for heat transfer. 2, we will know, we will have this factor of 3. You see, YCV in this case is 3 square root of mu x over u infinity. And you know where it came from. This is nu t, essentially. So we're going to say YCT is also a factor of 3. We're going to say it's a factor of 3. Okay. Now, what the other thing we're going to do is to say that in the viscous boundary layer, it developed all the way at velocities between 0 and u infinity. That's a viscous boundary layer. But here's the catch, and this is so important, and this is just so beautiful. And the book doesn't do it this way. So we would know then that the viscous boundary, the thermal boundary layer developed up to this point, right? YCT. What is the velocity at YCT? The velocity at YCT is much less than the velocity at the thickness of the thermal boundary layer is less, right? It's much less than the free stream velocity. And I'm going to call this velocity here, I'm going to call it UC, characteristic velocity. And if you see in this equation up here, we have alpha x over UC, not U infinity. Why not U infinity? Because the thermal boundary layer is very thin, and velocity very near the surface on a thin layer is very slow because it's stuck to the surface with a non-slip condition. So in the case of oils, for example, the transfer of heat from the plate into the oil happens all in a narrow range near the surface, in which the fluid is nearly stuck to the surface. Is smaller velocity. So there is some algebraic manipulations here, which you can follow yourself, but I got YCT here, that is the thickness of the thermal boundary layer. I make it square to forget about the square root, and I would get something that is, I get alpha x over u infinity, right? But sorry, so it's alpha x over uc. How can I calculate uc? How can I calculate uc? So I don't know what it is, but I can anticipate it. Let's do what I did here in this is all in the notes, right? And I'm going to give names to points. I'm going to name this point A. I'm going to name this point B. I'm gonna name this point C. And we got a triangle like when we did like similarity of triangles in high school, like kind of a Euclidean type of approach. And I'm going to go to this other triangle. And this is D. I'm going to call this point D, and I'm going to call this point E. Right? And we got those two triangles. And check out those triangles. I made this similarity. We can say, right, from knowing triangles, that this side DE is to EA. So DE is to EA, right? the same as BC over CA, right? BC over CA, because they're the same triangle, right? They share, they both are rectangular rectangular triangles, and they have the same angle. They share the same angle. Okay, so look at this. This is just triangles like high school, but these triangles have a meaning. DE is U infinity. DE is U infinity. EA is the thickness of the viscous boundary layer, is YCV here. Now we have BC, right? BC, and BC is UC, right? Well, I didn't know what it was, but I know it's this here. And CA is the thickness of the thermal boundary layer. So from this similarity of triangles, I can solve for the characteristic flow near the surface, right? Because we said heat transfer in oils happens very near the surface, where the velocity is very slowed down. Heat transfer in oils and thick fluids happen at very slow velocities when it's like dragging like molasses by near the surface. What is that velocity? This one here that we calculated. So we can say that instead of UC, I can write, using those triangles, I can write this relationship. U infinity, YCV, and YCT, right? It's U infinity and the thickness of the boundary layers. And then with a little bit of more algebra that you can do yourself, but you land here, that the ratio of thickness between boundary layers, between the thermal boundary layer and the viscous boundary layer, is Prandtl to the minus 1/3. Here, of course, you cannot remember this, but there's something that you will see coming up all the time. See this 1/3 exponent? When we did it for the case of the liquid metals, was 1/2, minus 1/2. And you're gonna see this happening all the time. And I wanted to go over this, so it's not magic to you. You don't take me on faith that the boundary layers are different. And when you take your class on mass transport, you'll already anticipate that there is also a different boundary layer for diffusion. And in addition, what we see is that depends on the type of fluid we have, whether it's very thermally conductive like molten metals, or very viscous, such as oils, we see that the ratio of boundary layers, not only one is thicker than the other, but we can anticipate it using the Prandtl number, but more. We can say that the ratio for the case of molten metals goes with Prandtl to the minus 1/2, but in the case of oils goes to a Prandtl to a minus 1/3. When you see these expressions tabulated in the book or in your professional practice, you'll see all the time expressions that have a Prandtl to the minus 1/3 or 1/3, depends on what it is, right? And you will know immediately that that comes from the ratio between the two boundary layer thicknesses for the case of viscous fluid. So people in ChE will see this exponent of Prandtl to the 1/3 all the time. And now you know it's not magic. It came from the ratio between the two boundary layers. And this applies to the case in which the boundary layer is, the thermal boundary layer is either very thin or comparable to the viscous boundary layer. You know what? That's the case for much thinner is a case of thermal boundary layer, much thinner than viscous is a case of oils for sure, water, and for being more or less one, which is the Reynolds analogy, is the case of gases. So water, oil, air, all fall in this 1/3 exponent. Now, if now we tabulate this with this thickness of boundary layer we determine, we can calculate H as we have learned to do. We can calculate Nusselt, and we can present a tabulation of this correlation. It's not a correlation, this is a derivation. This is not empirical. This is deeply scientific. And we would get Nusselt is Reynolds is a coefficient, Reynolds to the 1/2, Prandtl to the 1/3. I'm going to compare this with the previous one, the one we had obtained for liquid molten metals, right? Let's call it 0.6, right? Nusselt is 0.6, Reynolds to the 1/2, Prandtl to the 1/2. Look at this one here. Here we have 0.33, Reynolds to the 1/2, Prandtl to the 1/3. If you tell me nothing, I will know which is which now, because one is the 1/2 and the other is the 1/3. The 1/3 molten metals, almost never, unless you're working on nuclear reactors in submarines. 1/2 all the time, water, oil, air, argon, right? Like pretty much all gases behave similarly. This is the core of what's going on in convection. From here on, things just build up, and this was the pinnacle of the class. Now things will start getting a little bit easier. I want to tell you one more thing that is about the theory, and on Wednesday we're gonna do, I promise, an example that I feel is long overdue, and I owe you for that. But until we know what we're talking about, it's difficult to make examples. I want to discuss in these last couple minutes thermal boundary, turbulent boundary layers. So far, we were talking about laminar boundary layers, in which the equations are very simple. In turbulent boundary layers, we have all this turbulence, this microscopic motion that enhances transport. The number one thing to keep in mind is that we go from laminar to turbulent more or less gradually around a range. Now, for the practical purposes of this class, we're going to treat the problems as if they are 100% laminar until they become 100% turbulent. Reality is more complex than that. In reality, you have a transition region. But I think the class is already challenging enough as it is as to get into deeper subtleties. So we're going to say things are laminar, and we use formulas for laminar heat transfer until we hit a critical Reynolds number. And you know this from fluid mechanics. Up to the criterion for transition to turbulence is a Reynolds number. And once you hit this Reynolds number, then we are going to pretend everything is turbulent. I use the formulas for turbulent. Right at the transition, things are tricky. But you know what? Below the transition, we're safe, and above the transition, we'll be safe. And just at the transition, we are seldom going to be. So we're not going to fret much about it. This transition, this critical Reynolds number at which things go from laminar to turbulent, the way we see it in this class, that depends on the system. For the case of the flat plates we've been talking about, is this Reynolds critical that is calculated based on a characteristic length, right? And would be 5 times 10 to the 5. So here is the expression for Reynolds, and we have the velocity of the fluid. Here we have the kinematic viscosity of the fluid. When X is deep enough into the plate, then Reynolds will reach the critical Reynolds number, and from then on, we'll say that the plate is in turbulent regime. So next class, I'm going to discuss briefly the correlations and the behavior of the turbulent boundary layers, and we'll start talking about external flows. Let's stop here. I'll take a 10-minute break, and then I'll hold office hours like every Monday and Friday. Thank you very much, And I hope to see many of you later at 2.